Hello and welcome to exercise 6 from page 108, where we will be looking a little bit at slowly varying functions. So the definition of a slowly varying function L is this. We say that L is slowly varying if and only if for all positive constants C, L satisfies that when we evaluate it in Cx and divide by L evaluated in x, then this ratio tends towards 1 as x goes to infinity. Now, why do we call L slowly varying? Well, the reason here, as one of you interpreted quite eloquently during exercise sessions, is that this criteria tells us that L doesn't change that much as we go out into the tail of L, in the sense that the size of L of Cx compared to L of x is roughly of the same scale, and their ratio is therefore equal to 1 as we go out towards infinity. Another way that we can see this is by considering the relative difference of L of Cx and L of x compared to L of x as we go to infinity. So as we go towards infinity, the second term here is just equal to 1, no matter what. And the first term tends to 1. So this goes towards 0 as x goes to infinity. And this is a very nice way of interpreting what a slowly varying function is. It is a function where the relative difference in the tail between 2 points is equal to 0. Okay, so now we've gotten a bit more acquainted with what a slowly varying function is. Essentially, it's just a function that varies very slowly. But then we might ask ourselves, how do we characterize L? Which functions are slowly varying? And um, in order to do that, we can try to come with some suggestions, right? Let's try a log of x, for example. Our question is log of x slowly varying? And to answer that, we might try to plug it into the definition of slowly varying and see if it satisfies the condition. So we want to see if this ratio goes towards 1 as x goes to infinity. And we recall that the L'Hopital rule says that if the limit exists, then it's the same as the limit for the numerator differentiated over the denominator differentiated. So this gives us c over cx divided by 1 over x. And this is just equal to, well, the limit of 1 for x going to infinity, which is equal to 1. So in conclusion, log of x is slowly varying. We may also take a look at the definition again and ask further questions, such as if L is slowly varying, is 1 over L slowly varying? And to that extent, we may once again look at the definition, right? So we want to see if 1 over L satisfies the definition. So we want to look at 1 over L of Cx divided by 1 over L of x. Well, this is just equal to L of x divided by L of Cx, which goes to 1 since we have assumed that L is slowly varying, and thus this thing goes to 1 by assumption. So once again, we have that we know something more about how a slowly varying function may look. If we have something that's slowly varying, then its multiplicative inverse is also slowly varying. So we can also say that 1 divided by log x is slowly varying as well. And then we may ask, well, if we put a slowly varying function together with another slowly varying function by composing them, is that slowly varying? And so on and so on and so on. And we may continue this game more or less forever, trying to figure out how different slowly varying functions look. And after a long time, we might find out that they have some things in common and try to write that up using some kind of smart representation. And that is what we're going to look at in the first part of exercise 6. So in exercise 6a, what we are going to do is this. We're going to say the slowly varying function definition we have is not that descriptive. We cannot really use this definition to prove the statements that we like to prove about slowly varying functions. So in 6a, we will write up what we call the karamata representation of L. Of a slowly varying function. And this result is very nice. It says that for any slowly varying function L, you can represent it using this formula, where you have a function c0 of x multiplied by the exponential of the integral from some value x0 to x over epsilon of t divided by t dt, where we assume that c0 of x goes towards some positive constant c, and where we assume that epsilon of t is a function that tends towards 0 as t goes to infinity. So what we want to show is 6a is that if we have any function that can be written up as such, then that function is slowly varying. So what we'll be doing in 6a is showing that if we write a function up in this way here, then plug this function into the criteria for slowly varying, then it will satisfy that criteria. So what we'll be showing in 6a is this part of the karamata representation theorem. Now, the actual real interesting part of the karamata representation theorem is this part that tells us that no matter which function you have, as long as it's slowly varying, then you're able to write it up with this representation. Because, I mean, this is the part that's actually interesting, because that means that if I want to show something about a slowly varying function, then I can just write it up this way and show something about this function instead. And that is very useful. However, the proof that goes in this direction is a lot harder than the proof that goes in this direction, because when you do the proof in this direction, you have to figure out a lot of stuff, such as how do I construct C0? How do I construct epsilon? While I don't have any knowledge of how L actually looks. And it requires quite a bit of work. So we will not be doing the proof in that direction. However, I have included an attachment for you guys in the course homepage with that proof. It's a paper written by Resnick from 2005, which is really good and has a really nice proof of that. So we will be doing the proof only in this direction, if it's okay. So that was 6a, and in 6b, we will be making use of this very useful representation, where we say, show for a slowly varying function L. Well, what do we want to show? We want to show that for any delta greater than 0, L of x divided by x to the delta tends to 0 as x tends to infinity. And what does that mean? Well, that means we want to show that for any slowly varying function L, it can be shown that it does not grow quicker than x to the delta for any x to the delta. So it can always be subdued by a power function. That is what we will be showing in 6b. And to do that in 6b, we will make use of the karamata representation of L for the proof. So one video will be for 6a, one video will be for 6b. See you guys in the next videos.